Morning, everyone, and thanks for the invitation to talk to you today. So essentially, I'm going to be talking about crystallization and sort of in the process, you guys will get a feeling of my research work, but also I'll be trying to cover some of the unsolved questions that are still open in the area of crystallization. Now, crystallization is used as a process for separating materials. So if you have an impure solution, you can crystallize something, then you've got a solid and a liquid, so you can use standard solid-liquid separation techniques to get rid of the thing that you don't want. And thereby you've got the thing that you do want. In that process, crystallization is also a means of purifying substances. So, not unsurprisingly, industries like the pharmaceutical industry essentially use crystallization as a means of purification. And if you think about it, you certainly don't want nasty contaminants in the medicines that you take. So, having a process like crystallization to purify things is actually really important. We also have crystallization in areas like our bodies. So the process of an organism forming minerals is known as biomineralization. And this lovely image by Ernst Haeckel that you can see on the side here, he's literally drawn books of these things. They're pictures of corals, sponges, shells. A lot of these substances are in carbonate. The organism has created these minerals for a particular evolutionary purpose, for protection, for giving our body some rigidity. So our skeleton is a biomineralization process, as is our teeth. So biomineralization can be a good thing, but equally there's the not so good side of it. You can get gout, you can get kidney stones, you can get hardening of the arteries. So this is what's referred to as pathological biomineralization. And while kidney stones might be painful, they're not normally life-threatening, whereas something like hardening of the arteries can be. Interestingly, while we know that genetics plays a role, for most pathological mineralization, there's still a lot of open questions about how and why those pathological minerals get formed. So that's an area of active research for me and obviously of high interest. Now, in the lab, there's 4 common ways to actually form minerals, crystals. You can get 2 solutions which contain soluble species, mix them together, and you get a solid precipitate forming. So that's crystallization through reaction. You could have something that's melted, you cool it down, it solidifies. That's crystallization by cooling. You can evaporate off the solvent, and then what's left is more concentrated, forms crystals, or you could mix solvents. If the substance is soluble in one solvent but not in another, that's the anti-solvent. You can add the anti-solvent and you can force crystals to form. Now, with all crystallization, you have to have a driving force. In solution crystallization, that driving force is the supersaturation. Supersaturation is the concentration above the equilibrium solubility. Whereas if you're crystallizing from the melt, it's the temperature. So how far under the melting temperature are you? The degree of undercooling. Normally we interpret particularly solution crystallization through the classical nucleation theory, and I should say that the term classical here does not refer to the fact that there's some quantum theory out there. Classical is just because it's the oldest and most used theory for explaining crystallization. And essentially what that tells us is that when you're forming the bulk of the crystal, that is actually a negative Gibbs free energy, and it's related to the volume of the bulk that you're forming, whereas the surface costs you energy, and it's related to the surface area. So when you add those two Gibbs free energy components together, what you get is the critical radius. The critical radius says that you've got these metastable clusters in solution. If you are a little bit bigger than that critical radius, then you can minimise your Gibbs free energy by nucleating and growing. If you are slightly smaller than that critical nucleus, then you can minimise your Gibbs free energy by becoming smaller and redissolving. Implicit in classical nucleation theory is that the nucleus that forms has the same structure as the fully grown crystal. And the other implicit assumption in classical nucleation theory is that the solvent really, the only impact it's really having is that it determines the equilibrium solubility level. Not surprisingly, since then, there have been a few non-classical mechanisms that have been proposed. So there's the polymer-induced liquid precursor process, and this involves metal cations interacting with organic biopolymers. They come together, they form a dense liquid phase that initially forms an amorphous solid, and then that transforms into your crystalline product. The two-step process is essentially similar, except that you don't have any polymers involved or organic species. Then you've also got some non-classical growth mechanisms. Oriented attachment is where you've got small particles coming together and self-assembling into larger particles. They coalesce into a single crystal. And of course, this is a non-random process. It's oriented in some way. And mesocrystal formation is essentially similar, but the small nanoparticles or the smaller particles don't fuse together. On top of that, we have impurities or additives, depending on whether they're purposely added or not. So impurities can impact the rate at which you form particles or the nucleation. They can impact the size. So if they are impacting all the faces of the particles equally, they might just impact how big or small the particle grows to. They can affect the morphology, the shape. So if an impurity absorbs onto a particular face of the crystal, it will impact that growth rate, and so the shape of the crystal can be altered, sometimes quite significantly. Or an impurity might impact the polymorph. The polymorph is where you've got the same stoichiometry, but you have different packing arrangements of that particular solid. You might change the hydrate or the solvate that's formed. So if you have water, obviously, in your structure, that will be a hydrate. If you've got a different solvent in your structure, that will be a solvate. Altering the polymorph or the hydrate that you form implies that the nuclei that you start off with is different, or that somehow the crystallization process has been altered. So we sometimes understand how impurities impact that, and we sometimes don't. So that's a situation where there's still a lot more to learn about how impurities impact the polymorph that's formed. So here's some examples where calcium oxalate monohydrate is a solid that you find in kidney stones. Now, if you actually have some sugar and zinc into the solution, then what you have is clearly a lot fewer particles of the calcium oxalate monohydrate, and those particles are a lot bigger. You can change the shape of the particles formed. So left here, you've got barium sulfate that normally has this rectangular shape. As you increase the organic component, which in this case is a phosphonated calixarine, you change the shape of the particles that form quite dramatically. Similarly, in this case, you've got calcium oxalate monohydrate. In the presence of this calixarine-containing lysine, pardon me, you get these particles. You can do Raman and you can confirm that this is still calcium oxalate monohydrate, but the shape and size has been dramatically altered in the presence of this particular molecule. And then you can also change pardon me, the polymorph or the hydrate that's formed. So in this case, we've got some calcium carbonate that we formed, and we add magnesium ions. So we don't even have a complex organic molecule here. We've just got some magnesium ions. Initially, they change the shape of the calcite that we form, but as we go higher in concentration, we start forming aragonite. Right, so these pointy and kind of almost sheath-like particles here are aragonite. And actually, this is one of the unsolved mysteries still in the area of crystallization. We know that as the oceans of the world have increased their magnesium content, that we get more aragonite forms in shells and other sea organisms. But aragonite is less thermodynamically stable than calcite. So while we know that magnesium is involved in the formation of aragonite, why does the aragonite not dissolve away and form calcite over time? Still an open question. Similarly, we know that barium sulfate is undersaturated in the world's oceans, but there's still barium sulfate that you can find in the world's ocean. In fact, it's used as a proxy to tell you how productive the oceans of the world were in paleontology. On the right here, you've got calcium oxalate monohydrate, and in the presence of this particular organic, instead of calcium oxalate monohydrate, you now form calcium oxalate dihydrate. So I'll just finish up with one of the examples that I put up, and calcium carbonate. The idea here was to use infrared to monitor crystallization in situ. Why infrared? Because infrared gives you information about the environment that the species are in. There are issues with calcium carbonate though. The carbonate can have different speciation in solution, and there's a whole heap of different polymorphs of calcium carbonate you can form. On the plus side, there's a lot of research already, and you can use this data to characterise your solids. So for example, by looking at this low 700 region in combination with the 800 region of the infrared spectrum of the calcium carbonate that you form, you can tell whether you've got amorphous calcium carbonate, calcite, vaterite or aragonite. So you can use that information to your advantage. Now when you do spectroscopy and you want to monitor something over time, you don't want the crystallization to be over by the time you collect your first spectrum. So how do you kind of deal with that? Well, you can try and lower the concentration, and that should slow down the crystallization. But in doing that, you then might hit a detection limit issue. And actually finding this paper was a bit of a terrific moment, because in the case of calcium chloride and sodium carbonate, what you find is that at high concentrations, they form a gel. So I was able to use high concentrations of solution, which meant I didn't have a detection issue problem, plus the fact that it formed a gel meant that the diffusion kinetics and everything was slow. So I was able to collect quite a fair bit of timed data to see what was going on during the crystallisation of calcium carbonate. So I'll just quickly finish off. In essence, what you find is that calcium carbonate precipitates through a non-classical mechanism. You start off with amorphous calcium carbonate, which then transforms to vaterite, and it looks like in the process you also lose a bit of water. So I'll finish off because my 15 minutes are up. There's still lots to learn about crystallisation. There's, in terms of non-classical crystallisation, we have stable solution clusters, how much solvent is involved with those solution clusters, what you find in solution, does it have any relationship to what you then crystallise, and there's conflicting evidence there. Does that depend on whether the crystallisation is happening through a classical or a non-classical mechanism? What's the role of the solvent in general, and how can we predict the impact that the impurities have a priori without having to do experiments? All right. I want to thank all my students and collaborators that have worked with me, and I'm happy to answer any questions.